Welcome back, dear students. So, in the last session, we have discussed few properties of biomass, which is very important for energy production from biomass. So, in this session, we will cover the remaining characteristics of biomass. So, already we have covered physical properties like density, particle size distribution, permeability, moisture content. Then chemical properties, the two important one, that is proximate analysis and ultimate analysis. So all these things we have discussed in the last session. Now remaining properties are, one is the fusing point of ash. Then another important characteristics is the ligno-cellulosic composition of biomass. And finally, energy content of biomass. So all these three we have to discuss in today's session. So first we will discuss the fusing point of ash. So what do you mean by fusing point of ash? So as you know, the ash will be formed if you are using biomass in a gasifier, or if you are burning biomass in an incinerator or cook stove, etc. The residue formed will be ash. So this fusing point of ash, or which is also known as ash fusion temperature, AFT. So it is the most commonly used name for this property, ash fusion temperature, AFT. It is a temperature at which the ash resulting from burning the biomass forms a solid clinker by fusion and agglomeration. So it is the temperature at which this ash will start fusing, melting of ash will occur. So this will together join and will agglomerate. So that is the temperature, the starting point of this agglomeration. And this temperature is very important in the design and operation of especially gasification systems. In fixed bed and in fluidized bed gasifiers, the operating temperature of this gasifier must be lower than this AFT. So that is the first thing we have to understand. In fixed bed gasifiers and in fluidized bed gasifiers, the operating temperature should be less than this AFT, so that this AFT will not occur. But in entrained bed gasifier, that is a modern type gasifier in which high temperature is used and particle size is very less, the operating temperature should be greater than AFT. So why it is greater than AFT? So that the ash will melt and will flow down the walls of the gasifier and drain easily from the gasifier. So that is for entrained flow gasifier, which will reduce the slag related problems. And typical ash fusion temperatures are around 1100 degree to 1200 degrees. So this is the temperature, normal temperature range of ash fusion temperatures. It's 1100 to 1200 degrees Celsius. And how we can determine this AFT? We have two methods. Either we can experimentally determine using a furnace by measuring temperature, etc., or we can predict the ash fusion temperature by knowing the chemical composition of this biomass ash. So different biomass ash will have different chemical composition. Mainly the ash contains silicon dioxide, calcium oxide, potassium oxide, alumina, magnesium oxide, etc. So if you know what is the composition or percentage of these compounds in that ash, we can predict the ash fusion temperature using empirical relations. Otherwise we can determine using experimental, and this experimental test is known as the AFT test. And mainly we are in gasification, etc. If you have to study the effect of ash fusion temperature, we have to determine four temperatures, that is initial deformation temperature, softening temperature, hemispherical temperature, and flow temperature. So all these are related to our ash fusion temperature. So you can further refer these with the help of journals and textbook. So this is the importance of ash fusion temperature. Now another important property is the ligno-cellulosic composition of biomass. So you may know that every plant material and parts like stem, leaf, fruit, etc. are made of these four compounds, that is cellulose, hemicellulose, lignin and extractives. So every plant is made of these four compositions, that is cellulose, hemicellulose, lignin and extractives. Cellulose is a polysaccharide of linear glucose chains. So it is a polymer of glucose, straight chain glucose chains, and it is a main substance in the wall of plant cells, and this cellulose help the plant to remain stiff and upright. And while hemicellulose is different from cellulose, it consists of a short and highly branched chain of sugars. This molecular weight can be 50 to 200 times the basic unit. So it is slightly different from cellulose. It is not a straight chain. This highly cross-linked structure is there. And it is a polymer of 5 different sugars, which are D-xylose, D-ribinose, D-galactose, D-glucose and D-mannose, and uronic acid. So all these are organic compounds. So cellulose is just a polymer of glucose only, while hemicellulose consists of these 5 sugars and uronic acid. And the branched nature of hemicellulose renders it amorphous, and it is relatively easy to hydrolyze. So if you are using fermentation for producing enzymes from biomass, or if you are using anaerobic digestion in like biogas we will be anaerobically digesting this biomass to form methane and carbon dioxide. So in that case, this hemicellulose is very easy to hydrolyze. So hemicellulose we can very easy to hydrolyze compared to other cellulose and lignin. And what is lignin? Lignin is a non-carbohydrate polymer that encrusts the cell wall and cement the cell together. So lignin is a non-carbohydrate polymer which helps to cement the cells of plant, and it is very highly complex nature. And lignin is hydrophobic in nature. That means it does not conduct water. So that is why leaves, the surface of leaves etc. contains lignin. And the most important thing in our perspective is that lignin is the most slowly decomposing component of dead vegetation. So if you are using biomass for anaerobic digestion, that is for biogas production, this thing has to be considered. So if our plant material is made of mostly lignin, it is not suitable for energy production through anaerobic digestion. So this is very, very important. So we will discuss this in future. Then what is the extractives? Extractives is any substance that can be extracted from the plant using a solvent. So they include crude protein, oils. So certain plants, seeds, etc. will contain oil, starch, sugar and other thing. Anything that can be extracted using a solvent is known as extractives. So these are the 4 categories of plants based on their cell construction. So in this way, the only thing you remember is the hemicellulose. Hemicellulose is we can very easily hydrolyze and very easily we can decompose. so it is very good for anaerobic digestion. Then cellulose also, it will take time, but cellulose also we can digest, but lignin is not suitable for decomposition. Then there is a procedure for determining all these. This is a chemical engineering procedures are there. How to determine all these four quantities? So first we have to determine the extractives. So for this we have to take a dried sample, say some M0 gram, that is leached with benzene and ethanol mixture in the volume ratio of 2:1 at a fixed temperature for 3 hours. So first we have to determine the extractives. For that, this is to be leached with M0 gram, a known mass of biomass, is leached with benzene and ethanol mixture with the volume ratio of 2:1 for 3 hours. And after leaching, this is again dried in a hot air oven for 105 degrees Celsius for constant weight. So this will reduce the mass. The extractives will be vaporized and it will be reduce the weight. So the dried sample is again cooled in a desiccator and weighed. So it will be M1 gram. So after this procedure, initially it was M0 gram. After this procedure, it is reduced to M1 gram. So obviously the extractives, the percentage of extractives will be W1 will be M0 minus M1 divided by M0. So that is our percentage of extractives, M0 minus M1 by M0 into 100%. Then after that we will determine hemicellulose for the same sample, this M1 gram. So after the first procedure, the mass is M1 gram. So this is taken and it is this, after this residue is put in a flask with 150 ml sodium hydroxide solution, that is 20 gram per liter of sodium hydroxide. Then it is boiled with 3.4 hours, 3.5 hours with recycled distilled water. Then the residue is washed with distilled water till no sodium ion is present in washed liquor and dried it. And again it is cooled in a desiccator and weighed. So now after this second procedure, the weight will be reduced to M2 gram. So initially we have taken M0 gram. After extractive determination, it was reduced to M1 gram. So extractive is M0 minus M1 by M0. Then the M1 gram we have gone through the second procedure with sodium hydroxide. So it is reduced to M2 gram after drying and all other cool desiccant extraction. Then this hemicellulose will be W2, which is M1 minus M2 divided by M0 into 100%. So again the denominator we have the initial mass M0. So hemicellulose that is removed is M1 minus M2. So that is our ratio of hemicellulose. So now cellulose and lignin is remaining. The third we have to determine lignin. So for this we have to take about 1 gram of residue after the extractive analysis. So after the first step, that is extractive analysis, we have taken 1 gram from that residue. And this new weight is again cooled and dried, and it will be M3 gram, and it is mixed with 30 ml of sulfuric acid. So now we are using acid for removing lignin. 30 ml of sulfuric acid is 72% concentration and is kept at a temperature of 8 to 15 degrees Celsius for 24 hours. And this mixture is diluted with 300 ml of distilled water and again boiled with 1 hour with recycled distilled water. And again after cooling and filtration, this distilled water we have to filter it and cool it and wash again with so that no sulfate ion is present, using a 10% barium chloride solution. Sulfate ion can be identified using a 10% barium chloride solution, and it is dried, and this new weight after cooling and drying in desiccator, it is M4 gram. So then the mass personal lignin W3 will be M4 into 1 minus W1. We have taken 1 gram of mixture initially, then minus W1. W1 is extractives. We have removed already extractives. So extractives converted into fraction, that is small W1 is capital W1 by 100 divided by M3, because we have M3 gram after drying and cooling. So before this experiment we have taken M3 gram, it is M3 gram mass is there. So M4 into 1 minus W1 divided by M3 into 100%. So this is our lignin percentage. So we have to follow this a complex procedure. First we have to find out extractives, then we have to find out hemicellulose using sodium hydroxide. Now we are finding out lignin using sulfuric acid. So finally you don't have to do any procedure for cellulose, because it will be 100% minus sum of all these other 3%. So mass percentage of cellulose will be W4, we can say W4, which will be 100 minus W1 plus W2 plus W3. So this is the procedure for determining all these things. Now we are going to the last characteristics. So before that, this is an interesting cellulose, hemicellulose and lignin composition of some commonly used biomass taken from the textbook of Understanding Clean Energy and Fuel for Biomass from H.S. Mukunda. So here you can see, if you see coconut shell, one of our major biomass in Kerala, coconut shell, we can see 28% more, 28.7% is lignin. Cellulose is 36, hemicellulose is 25, and extraction, other oils are 9.3. So this means it is not suitable for, coconut shell is not suitable for anaerobic digestion, that is in biogas production, but it is suitable for gasification. So lignin content is high, more than 10%, means it is not that much suitable for anaerobic digestion. Similarly, coir pith also have high lignin content, 31.2%, so it is also not suitable. But if you see the rice husk, the last rice husk coming from rice factories, so only lignin is 14.3, so that much high. It has cellulose 31.3, hemicellulose 24.3, but it is also having ash content of 21.7. So it will be a rice husk will be, we can use it for anaerobic digestion also, mixing with water and other. So this is an important conclusion we are having. So looking at the lignin content, ash content, etc., we can say biomass is suitable for anaerobic digestion or other use. And the last one is energy content. So what is energy content? We are mainly looking for the calorific value or heating value of the biomass in energy content. What is heating value? Heating value of calorific value substance, that is heat released. Already we know that is the amount of heat released during combustion of a specified amount of it, and normally it will be for the liquid and solid fuels. It will be in kilojoule per kilogram or kilojoule per mole or kilocalorie per kilogram or BTU per pound. So all these units we can use for determining the energy content. But for gas, if you are looking for calorific value of gas, normally it will be in megajoule or kilojoule per normal meter cube. So instead of kilogram, it will be mostly in meter cube, and we can convert that into kilogram using the volume flow, etc. So this is our heating value, and we have two heating value. We already know higher heating value, HHV, which is also known as the gross calorific value. So what is higher heating value? If the products of combustion is bring back to the original pre-combustion temperature, and all the vapors are in condensed state, mainly water vapor will be present in combustion. So if it is in condensed state, that is, it is bring back to the original temperature, this will be higher heating value, because the heating value will be higher. This water vapor, etc., will reduce, will give this latent heat of vaporization to the calorific value, contribute that. So it will be a higher heating value. And on the this normally this temperature is standard temperature and pressure, that is 15 degrees Celsius. So not room temperature, not 30 degree. It is assumed that our products are at 15 degrees standard temperature and pressure. And what is lower heating value? Lower heating value is determined by subtracting the higher heating value and latent heat of vaporization, water vapor. So that means in lower heating value our product will be completely in vapor state. So especially water, the water is in vapor state, not condensed state. So it will be, we have to reduce the latent heat of water from the higher heating value. So we will be determining higher heating value experimentally, and we can calculate lower heating value by subtracting this latent heat of water. So here the energy required to vaporize water is not released as heat. So that is why it is less than higher heating value. Now we have to determine this for solid, and our biomass will be mostly solid or liquid conditions. The gaseous biomass is not that present. So it will be converted to gas only after gasification or some other process. So how to determine this calorific value or heating value of a solid or liquid biomass or any fuel? We have to use bomb calorimeter. So the instrument used for experimentally determining heating value of solid and liquid biomass is known as bomb calorimeter. So you can see this is the structure of bomb calorimeter. What are the parts? So mainly we have a bomb, which is a small case or small steel case for carrying this biomass. It will be inside. At the center we have a bomb, steel bomb, and that is having some fuse wires for ignition. We have to introduce ignition, so it will require a fuse wire for producing some charge. Then we have oxygen supply also is required, because it is inside a container. We have to supply the oxygen, good amount of oxygen. So oxygen at a particular pressure is to be supplied inside this bomb and the casing, and this is surrounded by a water bucket which have known mass of water. You can see here surrounding this bomb and this crucible we have a water bucket which have some known quantities of water, and we have provisions for stirring the water as well as measuring temperature of water using thermocouple or some thermometer, etc. And finally we have an outer casing with the insulated jacket. So this is the structure of a bomb calorimeter. So oxygen supply is required, similarly ignition wire is required, and a water bucket surrounding this bomb. So we have to burn a known amount of solid fuel. So what is the principle for this? So it is simply energy balance. So we will burn a known mass, say 1 gram of sample biomass, and the energy liberated is used for rising the temperature of water. So we can balance this, that is energy liberated is equal to energy gained by water and plus the energy gained by this container made of steel, and we can, from that we can get the calorific value of sample. So that is the principle. The energy or heat liberated by burning this sample is used for raising the temperature of certain quantities of water kept in a bucket, and heat absorbed by this is equal to heat released by the fuel or biomass. So this is an actual bomb calorimeter. You can see a crucible which is where we had placed the sample, 1 gram measured sample, and it is inside, we are inserted in a bomb, and we have an oxygen supply inside that bomb. Then that is placed again inside the water bucket, and which is again placed in a steel container. So mostly all of the material will be made of stainless steel, and we have provision for measuring temperature, etc. So what is the procedure? First, a 1 or maybe 1.5 or 1 known gram of biomass is placed in the bomb, and it is pressurized with excess pure oxygen, and it is submerged in a known volume of water, mostly 2 kilogram of water will be there, and it is electrically ignited, and this water bucket is put inside a steel container, and then it is ignited, and energy released by the combustion and heat flow is, so the energy is, it is burned, the energy is released, it crossed the stainless steel wall. So first it has to cross the stainless steel wall of this bomb, and it will increase the temperature of water jacket. So it will not purely increase the temperature of water jacket, it will contribute some heat is absorbed by this container of bomb also. It is made of stainless steel, it is having some heat capacity, so it will, this temperature also will increase, and we will measure this with thermometer, and when it is reaches an equilibrium temperature we can calculate the calorific value, and we have to, other than the specific heat of water, we have to add the heat capacity of the bomb material, because it will absorb also, the stainless steel will also absorb some heat, so we have to add the heat capacity of bomb material also, and some corrections are also to be made, because we have some electrical energy input is given initially for burning this ignition coil. Initiating burning we have to give some electrical energy, so we have to made some error correction for that by burning that fuse, and some acids will be produced also, and we have to titrate it with residual liquid, and we have to make some correction. And after, once the experiment is over, we can release the pressure by reducing the oxygen supply, and we have to check the bomb for, after experiment we have to check the bomb for any soot formation. So if there is some incomplete combustion, there will be some carbon soot or particles present inside the bomb. So if that is the case, we have to, again the test is to be repeated. So we have to, after the test we have to check for the bomb for any soot formation, because it will implies that there is an incomplete combustion.
And after the experiment, the interior surface of bomb is washed with a jet of distilled water. So we will wash it with distilled water, and this washings, or this distilled water after washing, is titrated with the standard sodium carbonate solution. Sodium carbonate solution with using methyl orange or red indicator. Normally 0.0709, so that much concentration of sodium carbonate solution is used for titration. And another thing, we have to find out the unburned piece of fuse wire. So unburned piece of fuse wire will be there inside the bomb, and we have to straighten that, and the combined length is subtracted from the initial length. Normally 10 centimeter will be the initial length of fuse wire. So we have, this is for finding out how much the energy contributed by the fuse wire. So we have to find out the burned wire length. So for that we have to subtract the original length of fuse wire, that is 10 centimeter. We have taken 10 centimeter of fuse wire initially. We have to minus that with the unburned fuse wire. So we will get the burned fuse wire length. So these are all required for error correction. Similarly, with the washings has to be analyzed for any sulfur content. So if there is a sulfur content present in these washings more than 0.1 percentage, we have to again do some error correction for that. So there are like 3 error corrections we have to do. One is for this fused wire contribution, another one is for this presence of sulfur, and another one is for the this titration, sodium carbonate, after sodium carbonate titration. So we will see how it is calculated based on this experiment. So suppose T1 is our initial temperature, that is before the ignition. T2 is final temperature, and C1 is milliliters of standard alkali solution, that is sodium carbonate solution used for acid titration, which is in milliliter. And C2 is percentage of sulfur in the sample, and C3 is the centimeters of fused wire consumed. So centimeter of fused wire, if C3 is centimeters of fused wire consumed. M is the mass of sample, normally it will be 1 gram. And now capital W requires the energy equivalent of calorimeter in calories per degree Celsius. So these are calculated in calories, and then we can convert into kilojoule or megajoule, etc. So W is the energy equivalent in calories per degree Celsius. So what is this W? Actually it will be the heat capacity of water plus heat capacity of the bomb material. So it will be mass of water. Suppose we have taken 2 kilogram of water, it will be 2 into specific heat of water in calorie per degree Celsius plus mass of bomb, this bomb material, into specific heat of that, it will be stainless steel bomb wall material. So this is a constant for a particular bomb. So if you are purchased for a particular bomb calorimeter, this capital W, the energy equivalent, will be given by the manufacturer or supplier. Actually this is the mass of water into specific heat of water plus mass of this bomb into specific heat of that material. So it will be supplied. Or we can calculate this also by using a non material whose heat, this calorific value is known, and normally a pellet of benzoic acid, which is not less than 0.9 gram or more than 1.25 gram is used. So this is not required if it is supplied by the manufacturer, or otherwise we have to determine this capital W. For this we have to use a known quantity of a particular fuel. Here we are use the pellet of benzoic acid, so it is having some calorific value, we know that. So using that we have to carry out the test, temperatures etc. we have to find out, and we have to back calculate the W value for future purpose. And by energy balance we can, this is a basic equation. We know that energy given by the biomass sample equal to this energy gained by the bomb plus water. So M into CV, capital M is the mass of sample, into calorific value will be this water energy equivalent into temperature change T, that is T2 minus T1 delta T. So CV, what will be the calorific value? It will be W into delta T divided by M. So this is the equation we can use, but some we already say that some error corrections are required. So 3 error correction. First, what is E1? E1 is the error correction for in calories for heat of formation of nitric acid, that is acid formation. We have titrated with sodium carbonate and we can say the acid formation. So error corresponding to that, so that will be C1 calories. Directly we can do C1 calories. So already we have defined what is C1. It is a milliliters of sodium carbonate solution used for titration. So that will, our E1 will be equal to C1, the milliliter of sodium carbonate used for titration. It is directly we can take it in calories. And E2 is the correction in calories for the sulfuric acid formation, that is due to the presence of sulfur, and it will be 13.7 into C2 into M calories. So this equation we can directly use. So E1, remember first one is the error correction for acid formation, that is mainly nitric acid formation. So it will be after this titration with sodium carbonate, we can say if you are using C1 milliliters of sodium carbonate for titration, this error correction will be equal to that C1 calories. Now if the sulfur is present in biomass more than 0.1 percentage, some sulfuric acid will be forming and we have to reduce that error also. So it will be 13.7 into C2 into M calories. This is some empirical equation where M is the mass of sample. Now finally E3 is the error correction for heat of combustion of fuse wire. We are burning some fuse wire for initial ignition, and it will be 2.3 into C3. C3 is the length in centimeter of burned fuse wire. It will be 2.3 C3 if we are using a nickel chromium fuse wire, and it will be 2.7 C3 if we are using an iron 34 BS gauge iron fuse wire, and finally it will be 0 if we are using platinum wire. So these 3 wires we are using mostly. So if we are using nickel chromium, and it will be 2.3 into C3, where C3 is the length of the burned fuse wire, and if we are using iron 34 BS gauge iron, it will be 2.7 C3. But if we are using platinum wire, it is very high good heat resistant quality. We can take it as 0. It's because not much the platinum wire will be burned. It is having high thermal conductivity etc. So it will be taken as 0. So after calculating all these 3 error correction, all these are in calories, E1, E2 and E3. We have to subtract this from our energy equation. So it will be calorific value after this error correction will be W, the heat capacity of our calorimeter, into delta T, temperature change, minus E1 minus C2 minus C3. So all these 3 we have to subtract, divided by our mass of the sample, capital M. So this will be our experimental equation for determining the calorific value. So W will be either given by the manufacturer or supplier, or we have to calculate W with the known quantities of benzoic acid. It's taken as a standard fuel sample. And we have to subtract E1, E2, E3. So this is a simple procedure for calculating the heating value of a solid or liquid biomass. So for gaseous biomass, we don't have to go for any experiment for determining this calorific value. If you know the composition of the gas, so what are the percentage of gas, what is carbon monoxide available, what is hydrogen, what is methane, etc. in a particular gas, we can calculate the heating value of that gas using equations. We know the standard heating value of hydrogen, we know the standard heating value of carbon monoxide, and carbon dioxide we cannot burn, so its heating value will be 0. So using that, we can, and knowing the composition of gas, we can calculate the heating value of a particular gaseous fuel. So we don't have to go for any experiment for that. So with this, we are stopping this our characterization of biomass session, and we will do some problems based on this. Thank you.